This is Equilibrium Calculations, Part 2. So far we've looked at examples in previous videos where we have some knowledge of the concentration at equilibrium. That allows us to determine the concentrations of the other species or the value of the equilibrium constant. How do you deal with situations when you don't have any information about what's present at equilibrium? Here's such a problem. We're given the equilibrium constant, and we're also given the initial concentrations of all of our reactants, and we don't have any products present. But we don't know anything about the equilibrium situation. How do we proceed now? So let's take a further dive into this question. The first thing I'm going to do is let X be the change in sulfur trioxide. If that's the case, it's going to go down by X. And similarly, the other reactant, which is in a 1-to-1 ratio, will also go down by X. The products will both go up, and also by a similar 1X, because every term in this expression has a 1-to-1-to-1 ratio. We now have expressions for what's present at equilibrium. Let's turn now to the equilibrium law expression. We have the products over the reactants. And now let's substitute in the values from our table. At first glance, solving this looks rather messy, with perhaps an x squared term or an x term, probably needing the quadratic equation. But we can avoid that by taking the square root of both sides. That will then simplify our work. So taking the square root, we arrive at the following. To get rid of that 0.028 minus x, we multiply both sides by that term, and it gives us the following. Take 3.55 and multiply it by both of the numbers in the expression, and we get this. Collect all the like terms, and we get 4.55x on the one side and 0.0994. Divide, and we solve for x. But we're not done yet. We're asked for the concentrations of all of the species at equilibrium. So we're going to substitute that value x into the equilibrium line. And that will give us the concentrations of the products as 0.022 and the concentrations of the reactants as 0.006. Let's look at another problem. Initially, we have 0.05 moles of each reactant placed in a 1 decimeter cube container. So that would give us the following information. Again, we don't know anything about any of the species at equilibrium. So we're going to let the change in oxygen be x. I'm going to choose oxygen here because it has the smallest coefficient. It's going to go down by x. And the other species will go down by 2x, and the product will go up by 2x. Again, maintaining the 1-to-2-to-2 ratio. At equilibrium then, we're going to make a simplifying assumption. Because we have a very, very small value of K, the change in those concentrations of our reactants will be very, very small. Now, what do we mean by a small K? Your teacher might give you a couple of ideas. Sometimes, basically, if K is 10 to the minus 4 or smaller, we can make this assumption. Or some employ what's called the rule of 100. If we take the initial concentration, 0.05, and divide it by the equilibrium constant, if that comes out to greater than 100, we can also make this assumption. But by making the assumption that the changes in our reactant concentration are small, we get the following line at equilibrium. And this will make our math considerably easier to work with. So again, we turn to the equilibrium law expression and substitute in our values. Let's clear the terms. Divide by 4 and take the square root, and we arrive at a value for x. Let's check out our assumption now by putting that value of x into our change in concentration. And we'll see that in the case of oxygen, for instance, 0.05 minus what we determined for x, it doesn't really change our value at equilibrium. And in a similar fashion, you could do this for nitrogen oxide, and you would get a similar result. With that in mind, we can therefore say that the concentration of nitrogen dioxide at equilibrium, which we were required to find, is going to be 2 times x, or 15 times 10 to the minus 6 moles per decimeter cubed. To summarize then, what we generally do in these situations, let X be the change in one of the substances. Generally, it's a good idea to choose the substance whose coefficient is 1. If K is small, make a simplifying assumption that the reactant concentrations won't change. Substitute into the equilibrium law and solve. And now use that value of X to solve for the variables in the equilibrium line. Thanks for watching.